So today I'm going to tell a story, and it ties back into malware analysis, I promise. But it's a story of when I first started getting to know computers and perusing around them. But before I get into it, if y'all would like, you can head over to ringzerolabs.com if you have any questions on this video or any of our other analysis. There's a lot of malware analysis posts on the site, as well as submission forms if you have any malware you'd like us to analyze. But for the story, where we start, when I first started getting into computers, what I would do is just browse around. I would browse and browse and browse. I would go through all different kinds of settings, figure out what they did. I would look at different properties of, the hidden tools in Windows at the time. What the disk cleanup does, what defragmenting the disk does, what error checking does, etc., etc. Go through hardware drivers, see how to install new hardware drivers. So I'd go through sharing options, as well as user authentication and ACLs and DACLs on the machine, and figuring out how all that works. I would also go through things that were a little odd, like this option down here, this compress this drive to save disk space. I'd click stuff like that and see what happens. And well, what happens is it does compress the disk, and it'll make everything smaller, but it makes things slower because everything is compressed, so it's having to uncompress things to access them. But the interesting thing is that when you compress everything, the files themselves, the text changes to blue, so it's no longer black. Just a random piece of information to have. And another random piece of information to have is if you go into the properties of files, and there's a little checkbox here, this encrypt contents to secure data. Well, if you do that on entire subdirectories and change all the files, the text of the files will change from black to green. And I was in a class a few years ago for a security certification, and the professor just asked, what does it mean if you see a file and the file name is blue? And I'm like, oh, well, that's it means the data is compressed. And he's like, what if it's green? Well, it's encrypted. And it's just random little tidbits of knowledge, and I just learned those things clicking around and getting to know the system. So that little backstory leads us to things like the system properties. So if you go to advanced system settings of the machine, there's a lot of different things you can do in here, like changing the name. So if you want to change the name and how it shows up on the network of the computer, you can change it here. If you need to do anything with devices or drivers, you come into the device manager. Advanced settings have a lot of things to do with the user profiles and different environment variables that you can set and things like that. System protection, you can turn off. System restore and speed up your computer a little bit if you don't need system restore. And then remote access sharing, etc. But in this advanced tab, I used to come in here quite a bit and come and mess around with the visual effects for Windows. So if you turn a lot of these things off, you get better performance in Windows. Or you can just let Windows choose for you, and it'll kind of measure your system performance and adjust accordingly. And then over here in advanced, this used to be a trick back in XP. You could, instead of letting the system automatically manage your page file, which is instead of physical RAM, what it is Windows just makes a file on your hard drive and uses that to swap things out of hardware memory onto the disk. And the disk, quote-unquote, memory is, of course, going to be slower than the random access memory, the chips that you put in your computer. But it does that to save room if you have a limited amount of RAM. So instead of letting Windows decide how big this page file should be, if you knew you had enough RAM, you could just, instead of it constantly changing the size of the page file on your hard drive and slowing things down, you could just set a fixed size, say, I want it to be 2 gigs, no more, no less, always. And that could speed up your system a little bit. So I'd come in here, I'd do things like that. But I would always get to this tab, Data Execution Prevention, and I never really knew what it did. I know that Windows says here, it protects you, but I didn't know how. So they include a handy little click here for the help menu and tells you all about DEP, or tells you a little bit about DEP. And it says that it can prevent damage to your computers from viruses and other security threats. Harmful programs can try to attack Windows by attempting to run code from your computer's memory. Yada yada, keeps going and going. But it's a very generic overview of what DEP is, and if you look up DEP online for more in-depth things, you can get a lot of detail on it. But what really helped me understand what this feature is and what it does and how it protects you is through debugging a program. So that's what we're going to do today. So roundabout way with an introductory story, but I wanted to show, getting to know your system and finding all of these random features can lead you to a better understanding of your environment, and that helps you with malware analysis, reverse engineering, exploit development, all of these things, because you can, one, identify what something is trying to do, or you can identify a goal that you want to accomplish. So today what we're going to look at is just an application that I compiled really quick. I think I got the source code from somewhere online. It's really easy. It's meant to be a crack me to show how buffer overflows work. And essentially all that happens is we have a vulnerable use of a function in this program. So the program will take input. The input is not validated in any kind of way, and it's simply passed to an argument, or not an argument, it's passed to a function without being checked. So the input we give it is passed to foo, foo takes it and string copies it into the buffer without checking the size or anything, which can lead to a buffer overflow. So that's all well and good, and trying to get execution of the program or get it to the function that it wants isn't the goal here. I'm just going to use it as a shell program to kind of show what DEP is and how it protects you. So if we take a look at the application in PE Studio and look at the optional header, we can see that ASLR, code integrity, and data execution prevention are turned off for this program. So it wasn't compiled with those safety features in mind, and that was on purpose by me. Most compilers now, or IDEs like Visual Studio and things, when they compile a program, they will compile it with these safety mechanisms turned on, but I specifically turned them off for this demonstration. So if we take a look at the program in X32 debug, and you go to debug and change command line, you can see here that I put in 16 A's, and 16 A's is the amount that this program can handle. If we go ahead and add another A, well, we won't do that now. I'll show you why. So we'll just stick with 16 A's. Then we'll go ahead and go, and I've already placed these breakpoints in the system, and we stop at 401390. And this is the foo function. So this is where our input ultimately ends up. So if we go ahead and step through this function with F8, and step and step and step, here in this little jump not equal, this little loop function, we can see on the stack here, the 616161, our input is being placed on the stack, and the stack is like a temporary memory space, so kind of like a scratch pad where functions can place arguments and things that it's going to use, and then when it no longer needs them, when the function returns out, that stack space is basically discarded. So here we can see that our input is being placed in that scratch pad, and we keep going, and there's 4 A's, there's another A, another A, another A, etc. until we finally get out of this loop. So now we see 16 A's, so there's 4 bytes, 4 bytes, 4 bytes, 4 bytes, 16 A's. And the reason I said it can handle 16 A's is because if we were to write a 17th A, what we would do is start to overwrite this address. And this address is where we are going to return after this function is complete. So if we go down, all those calls do is print output to this function, or to the program. But when we finally reach the end of the foo function, we're ready to return back to the code that actually called this function. And we see here that that return is right after all of our A's, and that's that 401, 400. And like I just said, if you placed a 17th A, it would look like this. There would be an A on the end of this address. And now it's not going to, the program is not going to return to the correct location. It's going to cause an error. So what this shows is that if we restart the program, we change the command line to add, change the command line to add 4 more A's, we should overwrite that return address. So we're going to come all the way down to the end here. Now we see we have 4, 8, 12, 16. And now we have 20 A's. And that overwrote our return function. So now if we try and return, it's going to try to return to address 61, 61, 61, etc. And that's an invalid address. It's going to cause an error. So if we place a correct address here, let's say the next stack address, the one that's directly below where all of our A's, our last A's were. So if we change this to 18FF3C, you can see that when we return, it's going to pop this address off into EIP here. And then you'll notice that the code section up here is going to change to this address here. So if we do that, if we step once, you can see now the EIP is at FF3C right there on our stack, and our code is pointing to FF3C. So if we look above, all the arguments that were pushed onto the stack are still there. They didn't disappear or anything. And if we were to then add some code to this, so let's just add some simple assembly. So XOR EAX with EAX, increment EAX, compare EAX to 5, jump not equal 0x FF3E. Oops. Type that wrong. 0x 28 FF3E. There we go. And that's it. So super simple assembly here. XORing EAX with itself just makes it 0. Incrementing EAX is just adding 1 to EAX, and then we're comparing EAX to 5. If it's not equal to 5, then we jump back to incrementing EAX by 1 and compare it again to 5. So this is a loop. It's going to loop until EAX equals 5 and then continue down the path. We don't really need to write anything else though. So this is equivalent to shellcode. So if an actor were to pass 16 A's with an address and then these bytes afterwards, what would happen is the program would read all the bytes. It would try to return from that foo function, and in this case it would return here to 18FF3C, and then start executing shellcode. Now this is a contrived example. This actually wouldn't work in most all instances because of this 00 right here. So if you pass in a string of all A's and then an address of, so hex bytes of 0018FF3C, the program would most likely terminate the string at this 00 because strings are null terminated. But for this instance, let's just pretend it works. You'll see why here in a moment. So we've returned to 18FF3C, that's here on our stack, and we've modified the bytes there to represent shellcode, let's just say. So if we start executing those bytes, we can see that EAX turned to zeros, cool. We increment EAX, cool. Compare it to 5, alright. It's not 5, so we're going to jump. And then we go through a little loop until EAX is 5, and now we continue on. So this is how a lot of exploits work with buffer overflows. They will overflow a buffer to gain control of EAP, and once they've gained control of EAP, they will have shellcode there to do something that they want. In this case, it's super benign. It's just, you know, a loop to compare EAX to 5, but it could do a lot worse things. Could monitor keystrokes, could install a backdoor, could do a whole bunch of stuff. But again, that's not really the point of this video either. The point is that this shellcode executed from the stack here. That's our temporary scratch space. Code should not be able to be allowed to execute from the stack. It's a very dangerous thing, and this is what DEP prevents. So as we saw before, this program was not compiled to enforce DEP, and the system only has data execution prevention turned on for essential Windows programs and services. My little program that we just ran is not an essential Windows service, so it's not going to enforce DEP. That's why the little bit of shellcode that we placed on the stack here was able to run, and we did not receive an error. So what we're going to do is turn DEP on for all services and programs. We're going to apply it, and that requires a restart. So while this is restarting, just to recap, the program itself that we ran does not have DEP enforced, nor does the operating system. So we're going to turn the option on in the operating system that enforces DEP on every single program that runs, except ones that we specify for it not to. Now, simply because we specified that the system has to enforce DEP on every single program that runs, that does not change the fact that this program was not compiled with DEP enabled. As you can see here, it's still not enabled. But when we debug the application, and we go, and we go, we go, we'll get back to the position we were just at. We can see that here are our 20 A's, and we have overwritten the return address. So again, we're going to change that just to the next stack address, so that we're just going to return right below it, just right next to it. And as soon as we do, this will execute. So if we step once, you can see that EAP is now the stack address, okay? And our code section is pointing to the bytes on the stack. So if we change these bytes like we just did before, so clear out EAX, increment it, compare EAX to 5, and jump not equal to 0x 18 FF3E. Okay. So our instruction that we're about to execute is this simple XOR EAX like we just did, and this code is on the stack. As you see here in red, I've edited those bytes just like we did before. And there's our 20 A's, there's the address we overwrote, there's our quote-unquote shellcode. If we step once, if you watch down here, in this bottom left-hand corner, what you should see is an error. Access violation. This is the same program, same shellcode that we just ran. As I just showed as well, dep is disabled for this program. But the Windows property for dep to be enabled on all system processes across the entire system is enabled, which means our little program here has it enabled by default. And that prevents shellcode from running on the stack. So if an actor were to do this kind of buffer overflow, gain execution of EAP somehow, again, I know this is a contrived example, but the process is still the same, and they get execution to shellcode on the stack, that shellcode will not execute because of dep. So I hope this makes sense. Again, this was a feature that I had ran into a long time ago and never really understood what it did. Even reading descriptions and everything, I never truly understood what it did until I tried to write an exploit and was getting just all kinds of errors, and I couldn't figure out why. It should have worked. It seemed to be working in the debugger, but just some mystery mechanism was causing it to fail. And that mystery mechanism was dep. So I hope this was informative. I hope you were able to follow along. I know this is a semi-complex subject when it gets to the stack and pivoting the stack and shellcode and all this stuff, but just take a step back, realize that the stack is just supposed to be a scratch pad. Things aren't supposed to be executed from it, and that if we're able to transfer execution to it, to a location that we control due to something like a buffer overflow, it can mean very bad things. But luckily there are things like dep that help protect us and keep the bad guys from getting into sensitive areas. So if you all have any questions on this video or any other of our videos, hit us up at ringzerolabs.com. We'd be happy to answer any questions you have.